Thank you very much. Sorry for the delay. I'm very happy to present today. I'm going to talk about understanding on the shoulder of foundation model. Let me start real quick with a small recap. What is a foundation? Okay, first problem. Okay, so what is a foundation model? Well, a foundation model is a large model, typically trained on massive amount of data, typically self-supervisedly, but it can be also with some sort of supervision. And one of the things is that over the years, these foundation models have been called robust estimator. Why that? Because we have noticed through a number of work that the representation that they've learned is transferable across task and domain. And in fact, a recent insight from a paper that will be published in ICML 24 from the team of Isola is showing that there is a correlation between the representation that learns a model trained on a single modality with other modalities. Here, what they show is that if you take a model, an NLP model trained on language only, the model that performs the best on language will have its representation somehow correlating with the representation learned by a vision model, here a Dino V2. And this is true for a small model like Dino small, but it's even more true the bigger the model is. And another insight that this paper provides is that when we look at model that aligns correctly with the vision, in fact, these same LLM model or the LSFAG that I said, I'll come back to that a bit after. And what they show here is that model that align. So we're talking about NLP models, so model trained only on language that align well with the vision here, or also the same model that are able to perform on the LSFAG data set. That is a common sense data set. Typically, it's a data set where an LLM model is asked to complete the sentence of a user. And what does it provide as an insight for us? Well, it actually shows that models that are trained on big data and tend to align regardless of the modality of which they are trained on. And beside, on top of that, they are somehow converging towards a representation of the word. And in fact, the same paper provides the plateau hypothesis, where they express that models are like the humans in the plateau's allegory, which are chained and looking only at a wall that shows the shadows of the external world. And somehow in this illustration, models are only seeing shadows of the word through the data they are being exposed to. And there are several parallels that we can do with that allegory. And the first thing is, as much as you increase the data in your training model, the more you increase the shadows for the observer, and the more they have a better view of the outside world, higher dimension perception of the outside world. And if you extend that analogy, we can take the parallel that adding a modality would be adding another source of light to our representation, to our word. And because you add another source of light to the observation that you have, you're providing with two viewpoints or more than two viewpoints of the same observation, and you're somehow slowly converging towards getting a true observation of the world. And this observation, we can see that in practice when we look at vision language model, which are typically a model trained on pairs of image and caption. That's famous now. And because they are trained on these paired data of image and text, they learn this multimodal embedding upon which we can navigate in order to increase either the language performance or the vision performance. And what I want to navigate through that talk is how can we benefit from the knowledge of this multimodal large model in order to improve the performance of scene understanding. And I could add here, how can we benefit from this knowledge? Being an academic that cannot train with spend 3 million or 10 million of dollars to train a large model. And the first thing that we can reflect on is that these models, they are learning a very wide space of the word, a very representation of the word. But in fact, that is that if you're taking the very traditional now in CVPR setup where you're trying to get the semantic segmentation of a urban scene, for example, in that case, or fishes, or even recognize some, right? So what you would care is that the model specialize somehow to your task in action. And how can we transfer that knowledge from the foundation model? Well, it's not super clear how it is being transferred. And an experiment that we have conducted with a student of mine is looking at a semantic segmentation task, where in that case, we take a backbone, here a ResNet 50, but we experimented a couple, and we pre-trained the ResNet 50 with either the ImageNet weights, we initialize it with the ImageNet weights, or either the clip weights in blue here. That, in that case, semantic segmentation. So we fine-tune it on a large, abundant scientific data set that is a GTA5, which is a game data set that provides dense labels. And taking this model, we now look at their performance across a variety of data sets, and these variety of data sets encompass a synthetic data set, but also real data set. All the other one are real, and also some data set that provide adverse condition at the bottom. And what we surprisingly note is that not only the ImageNet model is performing much better, but the CLIP model is actually performing quite badly, meaning that the performance or the robustness of CLIP has not been transferred to this new task. And we can repeat this experiment under different technical optimizer or different initialization condition, and we observe the same result. One of the assumption that we can make here is that we're distorting the CLIP features, so this is why the model tends to underperform in that condition. And in the first work that we'll talk about is FAMIX, a simple recipe for language generalized segmentation, all the questions that so in that work, what we try to solve is coming with a simple recipe to transfer the robustness that we have from the CLIP into a specialized domain generalized segmentation. And we build upon a previous work of ours that is called the PODA, where we introduce somehow an extension of this classical Adain normalization. And in that work, what we've done is we show that we can take a source image and process it through a CLIP image encoder, project the feature into this multimodal embedding, and by simply modifying the statistics of the first layer of the CLIP image encoder, we can make that embedding closer to those of a target embedding that is described with a prompt at the top, so driving at night. And in that case, we simply adjust the mu and sigma, so the mean and variance of the features channel-wise for only a single layer in the CLIP encoder. So the optimization is actually very, very simple. It's almost trivial. And it's also very light, a couple of iterations. It actually just is stochastic gradient descent with 100 optimization. And what we want to benefit from that prompt-driven instance normalization in the context of domain generalized segmentation. So how we apply that? The first ingredient of our recipe is to augment the features. We were applying the pin at the image level. Here we're applying the pin at the patch level, meaning that taken an input image, we extract the features of the feature map at the first layer of the CLIP embedding, and we simply cut this feature map into several non-overlapping spatial patch. And for each of the patch, we are able to augment it with our pin instance normalization. And the way we do that is by minimizing, again, a cosine distance loss, not with a specific prompt, because we don't have any information about our target domain, since we're in a domain generalization setting, but by simply using a random style prompt, which is in that case generated by ChatGPT. And on top of the random style prompt, we add the class name that is the dominant in that patch, in the current patch. And repeating, so having that with our pin component in the middle, we get a mu and sigma that correspond to the mu and sigma applied to get closer to that random style prompt. And we simply save that mu and sigma into a style bank, and we repeat that process for all the class in the current image and all the image in our current data set, right, in our source data set. Again, note that it's a random style, so we have, I think, something like 20 random styles that are different props. Okay, once we have our style bank, we want to use it for training our segmental model. And the way we introduce that is by introducing a component that we call an ingredient that we call the mixing, and then training the encoder by freezing part of the clip image encoder. And let's detail a bit the ingredient of mixing. So mixing here is the idea of mixing the style of the source style statistics. And we inspire from this work that is called mixed style, where they show that you can increase the robustness of a semantic segmentation network by interpolating between the style that we find in the source domain. And here, instead of applying it at the image level, we apply it patch-wise and channel-wise, and we extend that version of mixed style, that local version of this style, by interpolating not only between the source statistic, but also between the statistic of the source statistic and the augmented statistics, so the transformation that we have applied with our and when we can see that this simple ingredient is actually helping quite much, which it leads to an improvement of almost 20%. And it's a very simple channel-wise convex interpolation that we're doing, but it's still very efficient because we're bringing additional knowledge to the network. And finally, the third ingredient of our method, Famix, is to freeze partially the clip image encoder. Here, what we show is experimentally, we show that instead of optimizing or fine-tuning the full image encoder, we should simply fine-tune only the last layer of the last block of image encoder, which is this L4 prime value here. Because if we fine-tune the full network, it decreases a lot the performance. Quite likely because it distorts the clip feature, but that's only in conjecture. And the combination of all these ingredients create our Famix method, which stands for freeze, augment, and mix. And we can look a bit at some performance of Famix across data set. Again, we're looking at performance across 8 data sets. So any improvement is quite hard to get in average because it's an improvement in average over all the data sets. And while we report a number of all the baseline on the paper, I show only here the most competitive one. And you can see that our approach, Famix, is actually outperforming on all the data sets, all the baseline that exist, and especially note that the 2 baseline on the top, YNet and TLDR, use extra data. We can repeat the same experiment with a different backbone. In that case, RNet's 101, and we see even a bigger improvement. Let me show you a few qualitative results. So you can see that the Famix output, our method is actually less flickering than the baseline shed or the clip pre-trained. But it's still not a very cute semantic map. Remember that this is a zero-shot setting and domain generalized setting. So we don't have any information to fine-tune and get smoother semantic map. Now, a last element on Famix I wanted to highlight is the sensitivity to the prompt. We've seen that in order to optimize the representation and to make the representation closer to our target domain, hypothetical target domain, we use a random style prompt, right? So it was, for example, a urban style vegetation. So here we ablate this prompt, and instead of using, for example, a random style, we use directly random characters that are simply gibberish characters. And the surprising finding was actually those that are used to work with the ELMs or will maybe not find it so surprising, is that it's actually performed quite well, even with gibberish characters. And this has been actually showed by a few papers in the past on object detection, object classification, or even on segmentation. And this is somehow an insight that our component, the PIN component, is providing a stronger regularization and helps navigating around the structured language space. Okay, so that's all for the Famix part. I wanted to introduce an benefiting from foundation model, and the generative foundation model are very good at is generating very high quality, quite realistic images. And this has been used in a number of work that you can see below for training models that were shown to perform almost equal, sometimes even better than a model trained on real data. And this characteristic is actually something very convenient for tasks where it's very difficult to get correct set of data, correct set of images, which can be hallucinated by this model. And a typical task that we have performed with that type of model is a material estimation from images. Material estimation is the ability to estimate the function that transforms an input light into the output light refracted by the material, which forms what is called the BRI directional reflectance distribution function. And that models how a material appears in the image space or even to our eye. And when we talk about material, this is a single point material, but if you look at the material in 2D, so textured materials, the same model can, so we refer to that as SVPRDF. And SVPRDF is the idea of being able to decompose an image into several intrinsics. A typical model is the albedo normal roughness that we use in our work. And once we have this intrinsic decomposition, well, we can render the input material on any type of geometry or lighting with different types of input lighting and get a correct visualization of that material. And so getting this data, you have a number of data sets that provide synthetic data about that, but having real data to train our model on is actually quite complex because acquiring real SVPRDF requires a complex apparatus. Here you can see a setup for acquiring SVPRDF, or it requires very strong a priori about the geometry or the lighting of the image. Here, for example, is a work that estimates SVPRDF by using several flash images and using the prior of the location of the flash in order to reconstruct from the highlights of the flash, reconstruct the intrinsic decomposition, right? And a more recent work is Photomat, published at SciGraph 23, where instead of using several images, they use a single image with the prior that the flash highlights going to be in the very center of the image. Again, here in our case, we don't want to solve that with, you can see that these images are very close-up and orthogonal images, and they are not well ad hoc for training a model that will recognize material in the real world. And in our case, what we want to solve is the exact setup where we would take an input real-world image and extract the material from that images without having any prior about the geometry or the light. So this is a work named Material Palettes, the work of my PhD, Ivan, also in the back, and also collaboration with the University of Oxford. So as I said, the complexity of extracting materials from real-world images is that the material that we're observing is completely entangled in the scene. So it's entangled with the geometry. We don't know what is the geometry of the scene, and it's entangled with the lighting that we have. So a non-geometry and a non-lighting, the way we solve this problem is by a two-step approach, by first trying to disentangle this information of the geometry and lighting. So we could choose some kind of decomposition or estimation of geometry and lighting approach, but instead we want to rely on this foundational model. And what we do here is that for a given region input, we extract a certain number of crops and optimize LoRa dream booth, which is a stable diffusion, optimized very lightly with LoRa, with a given prompt that says an object with S star texture, where S star is the concept provided by the crops. And what that stable diffusion is optimizing for, it's optimizing for replicating this input region, or one of these crops, if you prefer, such that it matches this prompt. In the paper, we have laid this kind of prompt. As for all the prompt work, there's a lot of prompt engineering always required in the background. So once we have optimized our stable diffusion, we can use it with an input noise in order to generate a texture that resembles the one of the input region image. And in that case, we use a different prompt. The prompt is a realistic concept texture in top view. And again, this prompt is handcrafted in a way that the geometry and the lighting will be disentangled from the information of the generated image. And interesting insight is that the texture that we generate are tileable and high resolution. Why tileable? We use a concept introduced by Control Math and before by other paper, which is to roll the latent tensor by a random amount during the diffusion process. And we apply on top of that Poisson solving, which allows stitching together different types of texture image in a seamless manner. So that way we can get texture that are of any arbitrary size. Okay, we're not forced to generate only one texture from that input region. We can actually generate a number, as many as we want. And that's what we do. We generate a couple and we choose the most appropriate one by simply looking at the argmin of the LPIPs versus with respect to the crops of the input image. We can already evaluate that part of the pipeline, which is typically a texture extraction method to that point, so we don't yet have the materials. And you can see that we can evaluate it against the method that exists in the literature. Some are patch-based, so they have a square patch. You can see some of their performance there, and there is very little, actually one method that is using a region the same way as we do, so pixel-wise region, which is a DCV22. And what you can see on the right is that our texture actually looks more flat and less entangled in terms of geometry and lighting than the other baseline that you see on the left. This is especially visible, for example, with a giraffe skin that looks quite flat, which is exactly what we want. So now that we have a way to extract texture from an arbitrary image region, we want to be able to get the intrinsic decomposition, which is, in our case, the albedo normals roughness. And the question is how to do that. We have a number of data sets that exist that we can train on that are synthetic data sets, physically based rendering material library, like NCG or polyheaven or magnetic data, a model that will predict from an input image or provided by the material, by the data set, and that is trained in order to output in a multitask learning fashion, output the different intrinsics and penalize it very simply looking at the difference with the ground truth albedo normal roughness. And if we have that, we're able again to render on any kind of geometry or with any kind of lighting that we want. The problem is that if we train on these synthetic data set, there is a natural gap with the real data sets. These materials are synthetic and they don't really represent the high variance of the real materials. And so what we come up with is a new data set that we generate, which is a stable diffusion generated data set that is a high resolution and tileable texture data set that is composed of 9,000 assets covering around 130 classes. And because so we generate them the same way as I described before, but the difference with the current ambient CG data set is that these data sets that we generate provide information about the materials, but not intrinsic decomposition of the materials, right? So in order to adjust, and we come up with a domain adaptation strategy that I will go through it a bit quickly, but that trains supervisedly on the source data set, so the ambient CG or any other synthetic material data set, and unsupervisedly adjust to or adapt to the target data set, XSD, that present a lower domain gap with our data during the texture extraction. The way we do that is by leveraging some pseudo labels about the intrinsic decomposition and virtually rendering different lighting and penalizing this. Can go up in the details later in the question if you want. So now that we have this domain adaptation strategy, we can look at the complete pipeline of material palette. So we have an input image. We get some region proposal that can come from any method. It can be user-defined or it can be coming from a segmenter, for example. And for each of the region of this region proposed, we can extract a texture and decompose the texture in order to get the materials. And the outcome of this pipeline is that we get a real material palette of materials from the input image. So a few qualitative results, probably not very easy to see here. So we can combine material palette with one of these region proposals. So we can take, for example, materialistic that is specialized for segmenting materials, or SAM that is a classical segmenter, or directly the user-defined. And a few highlights here, look at the bricks, for example, here that are extracted correctly, although they are quite structured materials, which is often more harder than non-structured materials. And you can look, for example, at the leopard fur here, or the giraffe skin here, or the crocodile skin here. Some visual samples of bigger balls. And that allows seeing a bit better. For example, you can see that we can extract again these very highly textured materials. So now, how to evaluate that's only qualitative, but how to evaluate quantitatively the performance of our material extraction? This is not actually something easy, because there is no data set that provide an annotated intrinsic decomposition of all the material in this. Instead, what we do is we rely on an old data set. It's called Open Surface. Open Surface is a SciGraph 2013 data set that annotate region of an image that have the same material according to the user annotating. So it can be fabric, can be carpet, wood, marble. So we just know that this material in that region is supposed to be homogeneous, or at least the same material. We don't know the intrinsics, but we know the material. And what we propose is actually mapping this open surface data set with the ambient CG data set. So what we do is we map the ontology of the two data sets such that for each labeled region in the open surface data set, we can know what are the possible synthetic material that correspond to that material region in open surface. And we can run our method on open surface and extract materials with any of the region proposal method. OS mask stand for open surface. And you can see that we can compare the albedo, normal, and roughness of our extracted material with those of the corresponding class in the ambient CG dataset. And in with all the region proposal, we extract somehow a coherent material, which is verified by looking at a lower bound. The lower bound being the comparison of our extracted material. The lower bound being material corresponding to the ground truth class. So texture corresponding to the ground truth class, that are decomposed correctly. And the upper bound being the exact opposite, so not the ground truth class, so any class that corresponds to the non-ground truth class. Another way to evaluate is doing end-to-end rendering. So here we take some material, random material from open ambient CG. We apply that material directly on a 3D scene that has the complex geometry and lighting. We render the scene, and using the same region as where the material is being applied, highlighted in yellow, we can extract with our material palette the material in the region. And by comparing these two materials, we can get some kind of metrics. Here you can see the albedo, the albedo of the albedo, which is lower is better, which gets around 0.7, which can be compared with stable diffusion prompted version that is prompted with the ground truth class of the material used. So what we see here is that our material estimation is able to extract more correct materials than those being generated by a stable diffusion process. And again, we can compare also with materials that are extracted randomly in the ambient CG, so ground truth materials taken randomly among the ground truth class. So let me highlight a quick video showing the results. So we can take an input image, extract a material corresponding to a region, and since we have the material, we can apply it on a 3D scene. And why it's interesting to apply it on the 3D scene, because that's where you can see the defaults of the materials. Look at, for example, this leopard fur sofa that looks quite comfy and shows that the light interacts with the material quite nicely. Okay, and for the last part of my talk, I want to address a different topic, which is, can we align new modalities to existing foundation model? And this topic is actually quite of interest for modalities that are rare and difficult to acquire. A typical case, okay, hello? Okay, I'll continue like that, but for the remote, I don't know how I'll do it. A typical case that we can address is the fMRI data, because the fMRI data are very hard to and costly to acquire. And to illustrate what the fMRI or capturing, fMRI are capturing the brain activity of a patient during a certain amount of time, typically 3 seconds. And there are a couple of data sets that exist where patients are being shown an image, and we measure the brain, having compared the image shown to the patient to the brain activity. We can try to decode the brain activity in order to retrieve the image. And lucky enough for us, these images are often coming with from standard image data sets, so we can later retrieve the caption or the input image. The typical tasks that are being conducted on fMRI data or captioning tasks, where from the fMRI data, we try to get textual description of the scene viewed by the patient, or decoding, for example, where we try to reconstruct the image that the patient was seeing at the time of the fMRI. What we wanted to do is going a bit further is by aligning the fMRI with a multimodal large language model, we want to benefit from their capacity to handle different types of tasks. And especially, we want to be able to do brain grounding, which is the ability to caption an fMRI data, but also providing location of object and concepts present in the image. And I wanted to highlight that work because that's I could see also that in the workshop there was a highlight that vision should be applied for more social activity. And I think this one of the direction that we could go for vision, because this has a number of implications, particularly particularly to interact with disabled people that are or locked in patients. So one thing important to highlight when working on a brain is that the response of the brain varies across the subject. What it means is that the pattern that the pattern of the neural activity that is happening in your brain is different depending of the person, and if you typically models are currently trained per subject. Right? So anytime you have a new subject, you need to acquire a new large amount of data and retrain your. So this led to our work that we call the UMBAE, that's a collaboration with UCL and the University of Cambridge. And UMBAE stands for a Unified Multimodal Brain Encoding. I'll go a bit quickly through that work, just a highlight. And what we try to do here is designing a brain encoder that will be able to align with an existing multimodal large language model. So it can be a large language model or an MLLM. And the way we design it is that it can align with any sort of MLLM. And instead, well, we could align directly with the captioning version of the fMRI, because remember that these are COCO images, so we have their caption. We chose instead to align with the image encoder, which is ImageBind that I know was presented in the morning. What we want to do is designing learning and embedding that align with that image encoder, so that we are preserving also the spatial encoding in the fMRI data. So how we design our brain encoder. So again, remember that we don't want to be learning a model per subject, and we want to benefit from the cross-subject neural activity patterns. And we do that by relying on a universal perceived encoder and learning on top of that a number of subject tokenizers, so subject-specific tokenizer, which are being parameterized by a subject token provided to the model. And by training our tokenizer, this tokenizer, subject-specific tokenizer, act like an alignment towards an alignment to the cross-subject representation here in a bubble. And just mention about how to train this kind of model. One thing that we notice is that if we train simple with a normal batch, random batch, this type of model completely underperform. And one thing that we found is that we need to restrict or put a minimum of amount of data of the same user. So in that case, we select a user randomly and fill the batch with 50% of fMRI coming from that user, and the rest of the batch is filled in a stratified sampling manner from for the other user. And this simple technical trick improved already by 15%. So let's look at a few results. Okay. All right. Let's look at a few results here. These are brain captioning with our method UMBAE. And since we have aligned our brain representation towards the MLLM representation, we are inheriting from all their capacity. And in our case, which is allows interacting with the embedding through a prompt. And we can ask our model, describe this image. Image here represents the image embedding, not the image itself. We don't have the image, so it's an alignment of the fMRI embedding. So describe this image as simply as possible. And from the fMRI, the model is able to say that it's a person holding a tennis racket. And again, we can ask questions and interact with the model the same way as we would do with any MLA. And on the right, you can see our brain grounding task, which shows that from the fMRI embedding, we can get not only captioning, but also spatial reasoning about this. That's something very important if we think about robotic application, especially for disabled people. We need to know where they locate the object in the city. Going quickly to a few numbers, we evaluate on a large number of metrics in the paper. I'm reporting only a few metrics here. And here we evaluate on the captioning task, where we try to get a description of the scene viewed by the patient. And what is interesting to note is that we have two models. One is trained only on the data of user one, and one is Umbrae trained on all the user, which is 4 users available. And all the evaluation is done per user. So this is the evaluation only on the fMRI of user one. And what is interesting to note is though the Umbrae S1 model is more specialized to the actually benefit from cross-user information in the Umbrae model that is trained on all the users. Another task that we can evaluate, compose this baseline by taking fMRI data, applying some visual decoding on it from method that are currently existing, and now that we have an image, we can evaluate grounding with applying Shikron. A quick highlight of the result, you can see that Umbrae performed better, but what is interesting is we don't need the image representation, the middle image representation, so we perform also much faster. And the last slide that I want to highlight is adaptation to new users. Since we are aligned and we are training cross subjects, instead of having learned a user-specific representation, we have trained a representation and we have learned a representation that is across subjects. So we can now have a new capabilities, such as adding a user to our existing that we can use only by we train on the subject 2, 4, and 7, and we adapt to subject 1. And using only 5% of all the data, we can already get around 80% performance. And on the grounding task, we can get around the 90% performance.